Today is the fourth session in our climate and weather data for BC agriculture adaptation webinar series. While everyone is just joining, please feel free to introduce yourself in the chat box. I'm just going to start with a quick introduction to who we are, BC ACARN, the Agricultural Adaptation Research Network, if this is your first time joining us, and let you know a little bit more about the webinar series before we jump in with our speakers. So the BC Agricultural Climate Adaptation Research Network is a provincial network for climate change research in BC. And we formed about 3 years ago in 2017 with a mission to increase collaboration and to share expertise and resources across the province to better support both research and extension for agriculture adaptation. My name is Shauna McKinnon. I'm the coordinator for the network. And the network is also guided by a steering committee with representatives from the institutions that you see there, primarily the main academic agriculture research institutions across BC, as well as Agriculture and Agri-Food Canada, the BC Ministry of Agriculture. We have industry representation from the BC Agriculture Council, as well as the Climate Action Initiative. Starting this June, we developed this webinar series to provide a chance to get more in-depth information and personal tours of some of the climate and weather data tools that are out there. Climate and weather data is a cross-cutting issue if you're looking at agriculture adaptation, whether on the research side or applied on the farm. And there are a whole suite of tools out there, but it's hard to find all this information in one place. So we've had a chance over the series to look at tools available through Farm West, the Pacific Climate Impacts Consortium. 2 weeks ago, we had a tour of national portals, like climatedata.ca. Today, we'll be looking at some new technology for global data sets and new options for increasing data access. And then 2 weeks from now, we will have a session focused on tool support on-farm decision-making that are already being used in BC, including a regional agri-weather network set up in the BC Peace, the BC Decision Aid Support tool that is being used by Okanagan tree fruit growers to aid pest management, as well as a nutrient management tool that the province has developed. For all of these sessions, they're available, the recordings are available on bcacarn.com, as well as our YouTube channel. This session today will be recorded and you'll be able to find it there. We're also putting together a resource guide based on these recordings and information about each of the tools. So that will be coming on our website later this month. Also, you can register as a member of ACARN, joining over 400 people who are part of the network, including researchers, agriculture professionals, agrologists, government, producers and producer association members, all people who have this interest in agriculture adaptation and are looking to network with other people working in this space and be made aware of resources and events that are available. So I'm pleased to introduce today's session. Oftentimes when we're talking about climate and weather data in BC agriculture, the conversation can focus on what data gaps are we experiencing, what are the challenges, and today's session will really focus on what are some of the solutions and how can we use some of the newer technologies available to address these issues more effectively. Our presenters are Justin Huntington, who's a research professor in hydrology at the Desert Research Institute in Nevada. He's also the principal scientist for Climate Engine. Justin's background is in hydrology, evapotranspiration, irrigation, drought, hydrological modeling, all things that are really important in this climate change and agriculture space. And one of his key focuses in his applied work is looking at how to use new Earth observations and computer capabilities and modeling to better support research. So welcome, Justin. We're very happy to have you. And also joining us is Caleb White, who's the managing partner for Climate Engine and Habitat One. He's based in Ottawa, Canada. Caleb's background is really looking at user-centric web design and building data infrastructure. So for those of you that were on our webinar last time 2 weeks ago, Caleb was on the team that helped develop the climatedata.ca database and infrastructure. So you already have seen an example of the kind of projects that they work on. Also joining me today as a session host is Jessie Booker from the Pacific Climate Impacts Consortium. She's going to be helping with the moderation on the chat and the Q&A. Throughout the webinar, you're much encouraged to be asking questions, and we will be reserving time for discussion. So as you are listening to the presenters, please feel free to use the Q&A box to type in your questions. If you can put them in the Q&A, it's a little bit easier to keep track of people's questions. That also allows other people to vote up your questions. So if you want to also ask what someone else has already asked, feel free to vote it up, and we'll make sure that those questions are answered first. And for those that are just joining now, please just take a second to introduce yourself in the chat so we have a sense of who is on the live session today. It's always great to encourage, we like to know who's on the call and let other people know who's joining. So with that, I'm going to pass it over to Justin to begin. Thanks a lot.
Thanks so much, Shauna. Really pleasure to be with you all, and appreciate your time and interest in this. Let me share my screen here. All right, and go into presenter mode. If I could navigate here. All right, so you should be able to see everything. Is that right, Shauna?
Yep, it looks good.
Okay, perfect. Well, thanks again. Really appreciate your time. We're going to go through some new and exciting work that we've been doing with respect to cloud computing for advanced natural resource management and monitoring and decision support. There we go. Okay, so we've come a really long way since the launch of Landsat 5 in 1984, where essentially we were paying thousands of dollars per single image, date, roughly 125 by 125 kilometer image. And that price went down to about $600 an image all the way until 2009, until when the USGS decided to open up the whole Landsat archive for free as of 2009. And since then, the opportunities for space-based monitoring of Earth's surface has really skyrocketed. Landsat is the longest record of Earth observations that exists. So it's a really invaluable record that we have. It's open, it's free. And here we are today where we have not just Landsat, but constellations of satellites. We have gridded weather data. We have cloud computing. And as environmental researchers, we're kind of being bombarded with all these different data sets, different data formats, netcdf files coming out of our ears, and end up spending most of our time actually writing code to process this data instead of actually looking at the results and making good use of it. I started my professional career at the Nevada State Engineer's Office at the Division of Water Resources, and I didn't do much hydrology, actually. I did mostly a bunch of data crunching, looking at irrigated agriculture and trying to answer the simple question for the state engineer: how much water use occurs throughout the state of Nevada in irrigated agriculture? The legislature wanted to know that number, and so we started using Landsat to calculate evapotranspiration to get at consumptive water use across the state. And so, now that we have cloud computing, we have this ability to go from global, regional, and now field scale with Landsat, and now Sentinel-2A and Sentinel-2B, the European Space Agency satellites, to where we can really get at field level information and start to avoid downloading entire archives of data to answer simple questions like how much water use is there over irrigated lands, you know, how does riparian restoration projects look, you know, 10 years after those areas have been restored. Just all kinds of really neat answers that we can essentially obtain now at global, regional, and field scales. So this whole downloading of entire archives to answer simple questions. Here's a nice example of a small farming village in Gandhi, Ethiopia, where we're working with the Famine Early Warning System Network, FuseNet, to basically get a better handle on crop failure and risk. So this is what they had been using to look at crop failure risk is MODIS, normalized difference vegetation index. It's a measure of vegetation vigor in DVI, difference from average. And so to calculate this difference from average, you would have to download the whole entire MODIS archive, calculate that long-term average for whatever period you're interested in. In this case, September through February, and then difference the year of interest from this long-term climatology or long-term average. Also, the spatial resolution is obviously not very good. This is 500-meter spatial resolution. And now with Landsat, we can calculate that same anomaly map at 30-meter resolution, put that raster tile on a web viewer so that you can make that raster tile transparent and actually see what's underneath it, be able to zoom in, draw a polygon, get a time series out, and really start to pinpoint where fields are having trouble. So it's really a new paradigm for us in terms of having data available for free, having the cloud technology to actually make these computations on demand, and then having the new web technologies to actually visualize this information. So this whole concept of using the cloud, and really it is centered on bringing our algorithms to the data instead of the data to the algorithms. You know, in the past, we're just downloading gobs and gobs of data to our local systems. And, you know, the state agencies and actually federal government agencies, we just don't have the infrastructure to be able to handle literally petabytes of data to do this. So Google now ingests the whole Landsat archive, operationally MODIS, and many other satellite-based archives, as well as climate archives now, into their cloud. And Google Earth Engine is a massively parallel cloud computing platform in which they parallelize the computations where they break up the images by 256 by 256 pixel blocks, send those blocks out to thousands of computers or processors to process that data simultaneously, and then they stitch it all back together for you. So we don't have to handle the parallelization. Are there other cloud platforms? You bet. AWS, Azure. That said, they don't have the data catalogs, and they don't have this magical parallelization that we really need to have, as well as built-in functions. They have hundreds of built-in functions that we can use where we don't have to code that stuff up from scratch. So why the need for Climate Engine then if we have Google Earth Engine? Well, Google Earth Engine is great, but you have to know how to program in their API, application programming interface. And they have a JavaScript API. They also have a Python API. So there's still a pretty big block in order to be able to make these simple maps. Like here's an example of the standardized precipitation index. It's a drought map for the last couple of months, where we've basically reduced a couple hundred lines of code in Earth Engine down to a single command. It's an API call where we essentially packaged up all this code, and you're able to execute all this code in the back end to make this SPI map and then get it downloaded to your Google Drive or your Google Data Bucket in an operational way. So you can now make this command or turn this command into a cron job, and then send that cron job out every night to make this map and download it. And that's great too, but the reality is that people also want a web visualization platform. And so that's what we've developed. It's at climateengine.org. That's our homepage, which is currently being redesigned, working with Jamie Herring and Caleb White at Habitat One and climateengine.com, where we have this user interface where we can essentially make maps on the fly and make maps, download those maps, get time series, and also download those time series for many different assets. And I'll go through some of these. So here's just a simple land surface temperature map for June, July, and August of this year. It's a mean land surface temperature. And I made this morning in preparation for this talk. And then here is the difference from average land surface temperature for JJA of this year. So you can see just how anomalously warm it's been in the Southwest and Northeast. It's really amazing that we can make this on demand in just a matter of a few seconds. And I never had to touch the Modis archive. Now here's a trend of land surface temperature over the last 20 years for JJA. Now this is a new function that we just got in the Climate Engine. Given the feedback that we got from many users, they wanted to see trend maps. So this is a non-parametric slope. It's called send slope. And also we have programmed in a trend test using the man Kindle trend test function. So right now I'm showing all slopes at all significance levels. And now I'm going to show just the slopes where I have 90% confidence that they're statistically significant, or a p-value of 1 or 0.1 or less. So really amazing that I can calculate a non-parametric trend and then do a non-parametric trend test on the fly. And again, never had to download a single Modis image. Now I can clip and download this answer and then bring that answer as a GeoTIFF into ArcGIS or whatever other GIS platform I'd like. So a brief history of Climate Engine. How did we get started here? Essentially, we got started in 2014 through a Google grant. It was a Google Earth Engine Faculty Research Award, and we proposed to develop a site called Google Drought and get the latest and greatest drought indices into Google Earth Engine and make a cool little web UI for it. Now that turned into this a whole another project, really, where it wasn't just about drought, but also climate and land surface monitoring with Landsat and Modis and a lot of other different types of applications. We presented at the White House Water Summit in 2016. NOAA, the Bureau of Land Management, and USGS got really interested in this, as well as the Famine Early Warning System for applications abroad. And then all that rolled into a project called OpenET, or Open Evapotranspiration, which I'll give you a little demo of later. And nowadays, there's been a great influx of public and private sector interest where companies would like to use our API to operationally download products and then put those products on their, integrate those products into their own applications. And that's got us moving towards an enterprise build of Climate Engine, where we've essentially developed a software solution that can be deployed on your local system, as well as a commercial grade API where you can make the requests based on our API. So just real quick, available data product stats and things are growing. So the main two features of the application are maps and time series, where the time series, you can yank out time series for points, polygons, or custom features. With satellite data, we have Landsat, Sentinel, MODIS, spheres, GOES. We are working with Planet in a partnership with them to be able to explore Planet data and also purchase Planet data through the web application. And then as far as climate and weather data goes, a lot of different global data sets. That's obviously really important in Canada, where a lot of the data sets that we've been working with are just for the continental US. And it's really quite hard to find drought indices, drought indice maps for other parts of North America. So it's something that we've been focused on and would like to hear more from you on what data sets you would like to see added into this system as well. For variables, we have precipitation, solar, temp, humidity, wind, potential ET, land surface temperature, snow depth, snow water content, and more. And then the types of stats and drought indices, a whole host of different types of drought indices, including fire, and then statistical functions. So the newest edition that we actually have is the North American Drought Monitor in terms of our collaboration with drought.gov. There's been a lot of a widespread use of the US Drought Monitor across CONUS, but obviously there's need beyond, and to have a North America-wide drought monitor was really important, and important for us to get that into Climate Engine and expose that through the API and web interface. So in terms of kind of the software architecture, essentially the satellite and climate data goes into Earth Engine. Operationally, they handle all that ingest and maintenance, which is extremely convenient and takes a big burden off of all of us, both government, federal, state, local agencies, as well as researchers. And then we have our models, whether those are statistical models or physical models or whatever they may be, we can code them up in Earth Engine and apply all those codes across the whole entire image assets on Earth Engine. And then we spatially average whatever results we want across different features, whether they're states, counties, provinces, and create a geodatabase of those results, and then expose both the rasters and also the vector results through the API and also user interface. And so others can build web apps on top of the API for all these different types of applications. So why does Climate Engine matter for agencies? Well, we've been working with NOAA to get a good handle on this and getting their feedback. Essentially, their view is that it's a cloud native tool, and it's nice in that we can read NetCDF files from their Google Data Bucket, operate across those NetCDF files in the cloud, and then write back out to their Google Data Bucket. And they never have to touch or deal with the data on their end. Currently, they download massive amounts of data. They're one of the largest holders of climate data in the world, and they have to operationally maintain and update that data repository, and then run all their codes across those data repositories to, for example, create simple drought maps. So they see the great value here in just making a simple API call and download the answer, and instead of having to go end to end. Additionally, they really like the idea of just downloading the raster and then putting that raster into their own production pipeline. So here's a simple example where essentially the host, the data is essentially us. Then they download that data. They have a Conda and GDAL process where they convert those geotiffs into raster tiles, and then they host those raster tiles on a website. So here's just an example of that, where they're hitting the Climate Engine API with a simple command, a curl command here to download a drought map. They bring that geotiff into their pipeline, and then ultimately they put that raster tile on the NOAA Geo platform, which is an ArcGIS online platform. So here's just a really simple example of that, just a kind of a dummy test case example of the fact that this does work. One command, they can get a GeoTIFF, make a raster tile, display that raster tile on a simple leaflet map. So some use case examples that I'll go through, kind of interesting, and I'm going to focus on the Western U.S. here because that's where I'm most familiar with, and actually located right here in the corner of Nevada. This is a MODIS land surface temperature from difference from average map for the summer essentially of 2015, and I like this. I like to use land surface temperature difference maps a lot because it's really a reflection of the land surface energy balance. If you have hotter than average surface temperature, you're most likely to have drier than average surface conditions, hence the lack of evaporative cooling, which is why you have higher surface temperature. So when you don't have that soil moisture to evaporate, you're gonna have hotter than average surface because of that lack of evaporative cooling. Also, you can see a lot of fire scars here in California. And notice in northern Nevada, we had a cooler than average surface temperature, and that's because we had a wetter than average summer. So we had higher than average evaporation, causing that lower surface temperature, which is really intriguing. Now, at this this point in 2015, we're in the amidst of a deep hydrologic drought that started in 2012. And you can see here that there's different shades of red blobs here. These are essentially irrigated lands. And that top red blob is an area that's 100% reliant on surface water. There's no supplemental groundwater pumping. And so when the river goes dry, all diversions essentially get cut off. And so they were essentially fallow. Whereas this area down here, they have supplemental groundwater pumping. And so when they lack surface water, they pump groundwater. And that's why you don't see that big difference in surface temperature like you do up top. Notice we're surrounded by a sea of blue here, meaning that we had higher than average evaporation in the rangelands. And so that gets to this whole idea of having different and opposite signs of drought happening in the same place at the same time. And you may ask, well, how can that be? Well, this is that spot I spoke to where they didn't have any water to irrigate with from the river. And so you can see that at this Landsat scale, where this is a Landsat percent difference from average during the growing season of 2015, where you can see all these fallowed lands, but the rangeland was way greener than average because we had all that summer rain. And so this vegetative signal, the natural range kind of vegetative signal, is more on the line of like a 3 to 4 month type time scale, where if you get rain at the right time, you can really get a lot of great grasses to grow. But you still can't grow alfalfa because that requires a lot more water, and you need to get that water from the river. And so you can have hydrologic drought and vegetative drought happening, but they have opposite signs, where the vegetative drought is essentially non-existent, and it's opposite of drought. We had great grazing conditions, but the hydrologic drought was dire. The Bureau of Land Management at this time, they revoked all grazing permits, and that got the ranchers really, really upset. They talked to their congressional representative. It went back to DC, it came back to us, and they said, you know, you guys got to use best available science. There's grasses knee-high in this area. Why are you kicking the cows off the range? So that set up quite a conflict. And the reason is because the BLM was using the US Drought Monitor map to make these decisions. And the US Drought Monitor map at this time showed D4, which is the worst category. but the US drought monitor map is more of a hydrologic type map. It's a longer time scale map. And so you can have these wild swings in drought conditions that are not hydrologic driven, and are completely opposite to what the US drought monitor is showing. So important to understand the different timescales of drought and the fact that we can actually see it. Here is a nice trend map of land vegetation greenness, where red shows the decline in vegetation greenness over the last 35 years using the whole Landsat archive, and blue shows increased vegetation greenness. This is a little riparian strip in central Nevada where the channel has been eroding, the meadow and the groundwater levels have declined. There's a lot of grazing going on in this little meadow. And also we've had pinyon juniper woodland expansion in the headwaters. And so you can see that increase in greenness and then the decreasing in vegetation and greenness down in the lowlands. Also groundwater pumping and the drying up of springs and groundwater dependent ecosystems. So as you pump groundwater, that water comes from somewhere else ultimately. Conservation of mass. When you pump water from the ground, that water comes from somewhere else, and that somewhere else is a change in storage. And ultimately that change in storage in the aquifer starts to capture water at the surface, because you have to reduce the groundwater discharge if you're increasing the discharge in other places, i.e. groundwater pumping and evapotranspiration through growing crops. And so you can see all these wetlands and groundwater dependent ecosystems drying up as we are pumping groundwater. We do a lot of outreach and trainings. This is a training that we did with the Idaho Department of Water Resources. And also we do a lot of trainings with our international partners, and some nice testimonials here from our international partners, and the fact that essentially Climate Engine is a lightweight web-based user interface that doesn't require a lot of bandwidth. And so it's really great for African field scientists, for example, to get a handle on what's going on without having to download massive amounts of data or use ArcGIS that requires a lot of resources. And then just a nice testimonial here from senior remote scientist at Idaho Department of Water Resources. Climate Engine analyzed massive amounts of Landsat and climate data in a few minutes that would have otherwise taken weeks. And this is really important for a water right dispute, actually, where the grower was claiming injury. And in fact, that grower wasn't injured. Also working with tribal nations. So Navajo Nation, where we bring out a whole box of computers and work with tribal members to show them how they can use this new technology to improve natural resource management and monitoring across their nation. So we have an API, a beta version here with a URL shown at the top where you can download rasters. You can download time series as CSVs or JSONs or GeoJSONs, and we'll be implementing a new API here in the coming months that can operationally write to Google Data Buckets and G drives. So encourage you to register for the API if you'd like to kick the tires on this alpha version that we have right now. Also, a nice little high-level summary write-up on Climate Engine and why it matters on the Google Medium blog. So I'll share this presentation with you all, put the link in the chat when we go to discussion, and then you can go to these links. Some of the questions I'd like to ask, what data sets would be useful to add that may not be here? What types of use cases would be interesting to look at for you? What type of API requests that you would like to be made for operational government research and commercial applications? And then does being in the Google ecosystem cause problems for any of you being able to read and write from and to Google buckets and Google Drives? Some agencies don't have Google accounts. And so, being in a Google ecosystem can cause problems for some, and we'd like to hear about that. If you're interested in the publication for Climate Engine, we made the front cover of BAMS, the Bulletin of the American Meteorological Society, in November of 2017. So it's definitely searchable. It's open access, so it shouldn't be too hard to find. And here's our contact information up at the top. And I'd just like to acknowledge all our awesome team members and funding partners. I do want to give a couple demos now, and also open it up for questions. But want to do some demos really quick. Okay, so when you go to the application, there is a kind of a tour that you can take, which is nice. I won't do that right now, just in the interest of time. But the default settings here, we're kind of biased towards GridMet, and that our partners in the development of the application actually developed the GridMet dataset. The unfortunate thing with GridMet is that it's only for CONUS, because it does use the Prism precipitation product to downscale the NLDAS climate dataset. But we do have other data sets, like I mentioned, that do go into Canada. But what you just saw happen was it just summed up 60 days of precipitation layers in real time for the last 60 days, and it made that map. So for stuff that we have that goes into Canada, we have the North American Drought Monitor, as I mentioned. So I'm just going to show that really quick. Here's the August. So essentially last month's US Drought Monitor. They only update the North American Drought Monitor once a month, unfortunately, whereas the US Drought Monitor is updated once a week. And we can pull out a time series of the Drought Monitor raster values, which is kind of nice. So I'm going to put my marker right there and then pull out a time series going back. I don't know, we'll make this a little bit short in the interest of time. So it's going to pull out the time series of the monthly US or the North American Drought Monitor. So you can see that we got up to D3 in June, and then we dropped back down, and now we're back up on the rise. So that's kind of nice. You can also draw a polygon and do a spatial average on the fly and get that spatially averaged time series. And let me show some other data sets here for climate. We do have chirps. It doesn't go too far into Canada, unfortunately, but really one of the more commonly used data sets for international applications is MERA, MERA2. So with MERA2, we have quite a few different drought indices. The evaporative demand drought index is really cool. It is essentially I'm going to do the last month. It's essentially using the Penman-Monteith reference evapotranspiration equation and looking at anomalies within or anomalies of the American Society of Civil Engineers standardized Penman-Monteith. And the whole idea here is that if you have higher than average evaporative demand, that's probably because you have lower than average soil moisture conditions and hotter than average surface temperature and air temperature, like I described before. So it's kind of like this atmospheric land surface coupling process that really drives this. And so you can see this is a 1 month eddy, and I can make a 3 month eddy. So this is essentially a longer aggregation period. And the longer the aggregation period you get, the more hydrologic it becomes, like I was talking about before, where you can have a hydrologic drought, but actually have wet summer conditions, and those wet periods are a shorter type timescale. So we go all the way to 12 month with eddy, but let me go back to, let me make a 2 month eddy, and we can see some of these drought areas right on the US-Canadian border here. Let me do 1 month, and you can start to see little blobs start to show up here. And then now let me make a MODIS, land surface temperature anomaly, for the same area. I'm going to go to Terra daily, and then land surface temperature, and then difference from average. And yeah, sure, I'll just essentially do August. So this is going to take all the daily land surface temperature images from MODIS, calculate the long-term average from 2000 to 2020 for this August period, and then take the 2020 land surface temperature mean and subtract it from that long-term average. And so it's doing that all on the fly as we watch it. You can see, sure enough, this anomalously warm patch right where the North American Drought Monitor said we were dry. So it's really neat that we can start to kind of connect the dots in terms of the underlying processes driving drought, and then be able to quickly visualize it, and then ultimately download it. So now I'm going to download a map. So I'm going to say download this whole chunk right here, and I can name the file and then download map layer. So what this is going to do is, too big. Sorry. Let me download a smaller chunk here. Sure enough, you get an error when you're doing a demo. Okay, so it's going to send me to this URL, and then it's going to start downloading a zip file of this clipped geotiff. So really cool that I can do that. I'm going to go ahead and close that. And now what I'm going to do is make a Landsat NDVI map for the last June, July, August of this year, and calculate the mean and zoom in to near Calgary, where there's some irrigation to the east. So it's calculating the mean Landsat NDVI on the fly. And if this progress bar doesn't go away, just go ahead and hit cancel. If you see your map showing up, it's working on some pixels that aren't in the viewer. And so, yeah, let's go check out some agricultural lands here. Here's some center pivots. Voila. And now what I can do is, I'll just show you some features here really quick. So we have continuous and discrete color ramps, lots of different types of color ramps that you can make. We were having wrestling matches on what color ramp should be what. And so we were like, well, let's just add them all. And then folks can make whatever they want. You can also adjust the max and the min values. So some of the layers may look a little funky when they first display, probably because we don't have the max and min set exactly right to whatever aggregation and variable you're looking at. So let's just zoom in on this center pivot here, and let me draw a polygon around this center pivot, and see what this center pivot looks like. So this is the native time series, means it's the native time series of whatever image collection we're looking at. In this case, it's every 8 to 16 days with Landsat, depending on the combination of Landsat 5 or 7 or 8 for this time period. Or we can make a summary time series. So I'll show that functionality here in just a minute. But for the native time series, let me pull out, I'm going to pull out the last couple growing seasons here. And I should be able to see the crop development and harvest for this center pivot. So it's going to spatially average all those pixels within that box, and for every single date that I have an image, and it's going to make a time series of that spatial average. There we go. So it's a little noisy and to be expected since this is kind of a cloudy, one of the more cloudy areas compared to a lot of the areas that I work with in the state. But you can see the crop development and then harvest. This is snow cover, crop development, and then harvest, and probably some early snow, and then melt, and a little bit of green up afterwards. So, and then here we are currently. Looks like they harvested in about July. So really neat that we can check this kind of stuff out. Also, let's see, how am I doing on time? I'm getting a little short. Summary time series. Let me look at just the growing period here. I'll just do April through September. And I want to look at this, what this crop's been doing for the full growing period since 1984. So it's essentially going to plot the mean NDVI from April through September and show that every year, year after year. So you can see that they probably didn't grow anything in 2006 or some of these other years that have very low mean NDVI. So this time series is split by the mean, and I can change that right here and set this to 0 if I'd like. So you can see what years they're really productive in terms of their yield and greenness, and not so. So I better stop. I could keep playing for quite some time, as you could see, and turn it over to Caleb and then answer questions.
Thanks, Justin. Thanks so much for that. That's I always learn something new, which is exciting. So let me share my screen here, and we'll breeze through these pretty quickly because I want to get to some Q&A. Can you see that, Justin or Shauna?
Yes.
Okay.
Yes.
So following up from Justin, we got involved with Climate Engine about a year ago in the interests of operationalizing the world's best science. And I think what Justin showcased and what attracted us to working with Climate Engine and the team at DRI is that the nature of this problem is not going away for a lot of industries, and both in the public and the private sector. So in order to survive in the next 5, 10, 15, 20 years, we're going to have to operationalize the world's science in order to make advanced decision making. And that can be applied across a multitude of industries. And so when we got involved, we said, let's basically put the work that Justin and his team has done at DRI and scale it. So we basically create an enterprise version to satisfy the market and the demand that's happening right now for earth science data. Obviously, all facets of society are being impacted. I'll skip through this one. So what is Climate Engine Enterprise? So we've basically taken the APIs and the interface and given the ability for an enterprise deployment of Climate Engine. So we have basically two ways to look at it, and we're just in an alpha phase right now. So we're definitely looking for feedback from everybody. But it's a deployable solution to Google Cloud Platform. It obviously leverages Google Earth Engine, but we've built it with a lot of Google Cloud components to be able to ingest not only the data sets that are in Climate Engine, but also proprietary data sets and organizational data sets that may be internal to them. Basically satisfying the large big data problem for geospatial data sets, that not just the ones that are in Climate Engine, but proprietary and internal ones as well. And also including additional models from a scientific perspective that may or may not already be in Climate Engine, and giving the ability to provide recharge back to scientific organizations. Our belief is that we need to not only operationalize the world's best science, but also fund and have corporations and public institutions recognize that there's value in that data and value in the models and algorithms, and be able to provide a recharge back to the scientific community, because we all know that that community relies a lot on soft money, and there's an ability here to operationalize it and commercialize it if that is the goal. And ultimately, we're looking to deliver the insights required into client systems without needing as much domain experience in the science or in technology for that matter, in terms of wrangling massive data sets and delivering it through a streamlined API into any kind of system, internal or external. So one of the things I wanted to bring up today was any interest in collaborating. We'd be definitely open to having conversations. First on the data set ingestion. So Justin touched on it in terms of ingesting data sets that might be more relevant to Canada or global data sets or their use cases. We're in discussions with a few federal departments about getting some of the data sets that they use on a continual basis ingested in the climate engine. But would love to know from the audience or anybody in the community what they think we should be ingesting and how to make it better. Model ingestion. Obviously, there's a ton of models that are being used in Climate Engine, but we would love to know or hear from scientific community or scientific organizations about including some of their own work into Climate Engine and make this ecosystem work for the betterment of the planet, to be honest. And then for Climate Engine Enterprise, we're in an alpha stage right now where we could deploy a solution, and we're looking for alpha testers that may or may not be interested in exploring some of the features and benefits of having their own Climate Engine on their own cloud environment that they can then work with. And there's some debate around the table whether the most power will come from the APIs that we can stand up, or if it will be the actual cloud deployment on an institution's own cloud environment. So we'd love to have anybody's feedback on that, and definitely open to alpha testers. So with that, in the last 5 minutes, maybe Sean, I'll turn it back to you in terms of any Q&A.
Great. Well, thank you both, Justin and Caleb. That was a very dense, information-packed presentations. There's one question in the Q&A, and I invite people now to think about how they could use these applications, or questions you have about how to use the existing Climate Engine tool, and type in your questions. I'll start with one going back to Justin, the demo that you gave. Are there soil moisture layers available in those data sets there?
Yeah, there are. Yeah, let me just share my screen really quick. It's something that we've been working on adding. I'm not totally satisfied with what we have so far, to be honest. Let me show you. This is kind of scary. The more I zoom out, the more it's going to process Landsat data. So until you restart, it will just keep cranking on whatever your last request was. But let me show you here. So climate and hydrology, these data sets down at the bottom, land surface. So FLDAS is a NASA product. It's similar to the land data assimilation system, but it was really meant for famine early warning. But we do have soil moisture at 10 centimeters, and then this more integrated 0 to 100. So I'll just make that average for the values for the last, well, let's do JJA, and it will plot up soil moisture. One thing you can see here is this discontinuity in the grid, the modeling grid that NASA's using. So that's kind of unfortunate, but it's what we have to work with, and then we can make a difference from average condition. And because the latest data set we have is 8.1, unfortunately, I'm going to change this to 801 and change this to 2020. but I can make an anomaly map of soil moisture. One of the things that we are working on is trying to get lower latency from NASA to Earth Engine and then to us. So it's definitely something we're working on with respect to latency, but we can make anomaly maps of soil moisture. It's just they aren't exactly real pretty because of this discontinuity. If there are other soil moisture products that are out there that you'd like to see in here, definitely let us know, because we are wanting to get more soil moisture products. And LDAS has a soil moisture product through their land surface model VIC and NOAA, but it doesn't go that far into Canada, unfortunately.
We can go a few minutes over the hour, so if people want to stay on and they have more questions, feel free to ask them. One of the questions I wanted to bring up is the question around the usability of Google Earth tools or Google tools, the Google ecosystem, as you said. So from a Canadian perspective, for accessing data through climateengine.org, that's very straightforward. But where it becomes stickier, of course, is for Canadian institutions or academic purposes. There can be challenges in terms of data privacy, data security, data storage for using these tools. So it'd be great if you could address that, because I know that's a question that's come up in the past.
Yeah, for sure. So one of the things that we're working, one of the organizations obviously working closely with is Google. And they just got their protected B status in relation to the federal government of Canada. So they can control for secure environments and secure data. And so happy to have a conversation if anybody's interested in syncing up on that front. But the short answer is yes, it can be secure, both for data at rest and in transit. So it does satisfy the kind of residency problem of data. So there's more to come on that, but and I would leave it definitely to a cloud engineer that is specialized in security, but it does meet the qualifications for protected B under the federal government of Canada. So that should satisfy most of the use cases out there, unless it gets into some more detailed needs, which we can chat about.
Great, thanks for that answer. Okay, so another question we have from our participant is around radar data. So are the radar data, Sentinel-1, available for being processed in the future? Some of the studies show radar data potential for monitoring soil or vegetation through the polarimetric techniques. Justin, I think that's for you.
That's one for Justin, for sure.
That's an excellent question and suggestion. There are radar data available within the Google Earth Engine data catalog, specifically Sentinel-1. And it would be great to integrate that in the Climate Engine. So far, we've just been focused on the optical data collections, but radar, as you pointed out, has a lot of really useful applications for vegetation monitoring. It's a little noisy and sometimes hard to interpret, but as you said, you know, applying models to essentially convert the radar data into something meaningful is where we need to go. So that's a great suggestion, and it's I think we should put it higher on our priority list for sure.
One of the other things I'll add just in terms of color to that is that from a proprietary data perspective, that's one thing that we're really focused on as well, is not just integrating with the data sources that are in Google Earth Engine, but pulling in other data sources, external Google Earth Engine to create this, you know, interoperability and solve some of the data and the big data challenges that are out there for organizations. Notwithstanding procurement of those proprietary data sets if the use case you know, necessitates it. And on the radar data, there's some interesting things happening in the commercial space with organizations like Capella Space or ISI over in Europe, that it's definitely on our roadmap in the next 24 months to start integrating more and more of those data sources, and radar being one of them.
And Caleb, could those data sets be integrated into climateengine.org as it stands now, or would that be for new applications?
So it'd be both. So what we're going to do in the course of the next probably 2 to 3 quarters is stand up a climateengine.com that has the ability, because obviously if it's proprietary data, there's going to be a charge there for it. So we need to have a commercial conduit in order to supply that data feed either as an API or as a solution, and have that recharge go back to the commercial data providers. So the short answer is yes. The long answer is it's going to be done from a commercial perspective under climateengine.com.
And for academic researchers or others that are working with data sets that aren't publicly available but could be open source and free of charge, would they be able to contribute data?
Yes. Yep. And actually, on that note, what's interesting is Justin mentioned it, that we've integrated with Planet Labs. We're one of their gold partners here in Canada. And they're very, very interested in helping find use cases and finding, I mean, they're providing raw data, which is great for some use cases, but for the majority of use cases, we need the insights off of that data. So typically there's some sort of post-processing or models applied to the raw data that then comes out with, an insight from a data analytics perspective. So we've been working closely with them and actually have, and will be launching in the coming weeks, an open data set that is derived from Planet data to do some analysis on. So from a researcher perspective, it will showcase, it's sort of this chicken and the egg thing. I need to kind of have the data and see what I can do with it before I buy it, versus I'm going to buy it all and then find out I can't really use it. So we're trying to match that and try to work in between the gray area there, where we can give a little bit of data from them and work with Planet to release a little bit more of that data to show some of these use cases and show the differences. To get down to, I mean, Justin was talking about Landsat and Sentinel getting down to 10, 30 or 10 meters, but Planet's getting down to 3 meters or even sub-meter now, and, like a lot of other commercial sources. So for certain use cases, it makes sense to look at that data, but we just want to help facilitate what the ROI and where the value is to doing that.
I really apologize, Shauna and everybody, because I went over, but I'm 5 minutes late on my next call with Planet, actually. So I better hop off. But really, really, thank you for having us. And if there are any questions that I need to field, just feel free to reach out to me, Shauna and Caleb, and via email, and I'll try to answer. But thanks again for having me, and look forward to seeing you all hopefully in the future. Thanks.
Great, thank you very much, Justin. I do just have one last question that Caleb, hopefully you could answer. So for Climate Engine, does it just handle, or does it handle any near real-time weather data, or is it mainly historical data?
Good question. I know that it's at least weekly, if not daily. So, and there's also some interesting things happening from a seasonal or sub-seasonal forecasting perspective. So again, we're just looking to include as much as we can in here to get the world's available science embedded in the platform, and that's definitely a key piece of it. So we can definitely follow up after the fact to confirm it if somebody or whoever asked the question wants to email and reach out. But that would be my best guess, is that it's at least weekly, if not daily.
Okay, great. Well, thank you so much. Thank you everyone for joining today. Thank you, Caleb. This has been a really interesting session, and look forward to seeing what you guys do in the future.
Yeah, well, thanks everybody for attending, and thanks for everybody for your time, and Shauna and Jesse for your support. And if there's any questions following up, by all means, my email is there, so feel free to reach out and we can chat further.